Hey, welcome everyone. So we're very happy this week to have Petar Veličković. He's a senior research scientist at DeepMind, and prior to that, he was a PhD student at the University of Cambridge with Petar Veličković. And his research interests are on geometric deep learning, and in fact, he's written a book with the same name. And I think he's going to talk about this today. So thank you very much, Petar, and yeah, please start.
All right. Yeah, thank you so much for the fine introduction, Matthew, and thank you so much for having me. I'm sorry I had to cancel the initial time I was giving this talk. I hope that I hope that you will find the content of my talk today interesting. We're going to be talking about geometric deep learning. Before we kind of dive into geometric deep learning per se, I would like to just introduce the broader context behind geometric deep learning and why deep learning practitioners in general should be looking at geometry during their day-to-day work. And to demonstrate this, I'm actually going to take you back in time. And when I mean back in time, I mean way back in time. For example, back in the time of Euclid, 300 years BC. Now, Euclid, as you might know, is the founder of Euclidean geometry, which for many years was the way to do geometry, because simply no other geometries had existed. And through a very simple set of guiding principles or postulates, you could derive all of the essential rules that governed the Euclidean geometry. And for many years, this was the status quo. This drastically started changing in the 1800s. This was a super exciting time to be studying geometry because several mathematicians, in their efforts to show that Euclidean geometry is the one true geometry, started by assuming that one of Euclid's postulates was false and then trying to derive a contradiction. But instead of deriving a contradiction, they ended up deriving a completely consistent set of alternate geometries where that completely supported all of the other axioms, and you ended up with completely different, very interesting phenomena. So some prominent early examples include the hyperbolic geometry of Lobachevsky and Bolyai, and the elliptic geometry of Riemann. Now, what you had as kind of a state of the field of geometry in the 1800s was you had a lot of these competing geometries being proposed, all of them with their own set of rules, terminologies, and so on. And naturally, this begged the question of, what is the one true geometry? What is the geometry that I should be looking at? The solution to this problem, well, the foundations for the solution to this problem were laid about 20 years later through the work of a young German mathematician by the name of Felix Klein, who had just been appointed to a professorship position at the University of Erlangen in Germany. And he actually proposed what is now known as the Erlangen program, where he showed that actually you could look at the geometries in a very unified manner if you studied them through the lens of invariances and symmetries. So what are the transformations which under this geometry leave an object invariant or unchanged? And he further demonstrated how we could use the language of group theory to formalize all of this. And it cannot be overstated how much of an impact this had to mathematics. In terms of geometry, especially through follow-up work of Élie Cartan, all of these competing geometries in the 1800s were unified under this lens of group theory, which meant you didn't really need to hunt for the one true geometry anymore. All you needed to do was decide on a domain and decide a set of symmetries that you wanted to be invariant to, and this was sufficient to define all the rules of your geometry. But beyond the impact it had in mathematics, it also had a massive spillover to physics, where it stimulated the work of Emmy Noether, wherein through Noether's theorem, it was shown that all conservation laws in physics can be derived through the principles of symmetry, and it even enabled the classification of some elementary particles. So essentially, one of the most important results in all of physics was a direct consequence of the Erlangen program. And on the theoretical computer science side, category theory is a language that is often used to formalize various concepts in theoretical computer science. And through the very words of the creators of category theory, you can look at that entire field as a continuation of Felix Klein's Erlangen program. So this seemingly isolated idea of unifying a lot of various geometries through a common lens of invariance and symmetry had amazing transformative effects in various areas across the sciences. And now fast forward to, say, the year 2020, and a lot of us are doing research in the area of deep learning. And if you look at what the state of the art in deep learning looks like nowadays, left, right, and center, people are proposing various kinds of architectures for dealing with various kinds of problems in machine learning. And these kinds of architectures often come with very broad sounding statements, such as most architectures can be seen as a special case of a convolutional neural network. Everything, when you abstract far enough, can be seen as a graph. Therefore, graph neural networks are a quite good abstraction of all these architectures. Transformers leverage self-attention mechanisms, and attention is all you need. And long short-term memories are Turing complete, so why would you ever need anything else? So this obviously begs the question, what is the one true architecture? Because you have all of these different fields and niches proposing their own unifying architectures, which claim to be the architecture that the people should be looking at. And often it's not very clear what is the one true architecture people should be looking at. And in many ways, I think the state of the art in deep learning in 2020 feels a lot like geometry must have felt in the 1800s. And if history is to teach us anything, it's that now is the right time to be looking at the various geometric principles that might be underlying these architectures. And through such an effort, in the spirit of the Erlangen program, we may try to rederive all these popular geometric architectures. And as a result, now it's our turn to study geometry. So my name is Petar Veličković. I'm a senior research scientist at DeepMind, and alongside Michael Bronstein, Jean Bruna, and Taco Cohen, we have set out to do exactly this, to study the current state-of-the-art landscape of deep learning through the lens of geometry, invariance, and symmetry. And we have formalized our findings in a book, Geometric Deep Learning on Grids, Groups, Graphs, Geodesics, and Gauges, which I'll be talking to you about in this talk today. So before diving into the specifics of geometric deep learning and how it can help us as a unifier, just a quick recap on the essence of deep learning nowadays and why it's a fundamentally hard problem. So what we commonly want to do in machine learning and deep learning specifically is to fit a curve to a set of points in a training set in a way that generalizes decently. And often, specifically, what we want to do in deep learning is to do this in a very high dimensional space. And what happens in a high dimensional space is it turns out that this is a very hard, even cursed estimation problem. Even if you restrict yourself to a set of very simple target functions, such as the one Lipschitz functions, you can easily construct a very painful counterexample, such as this spiky Lipschitz ball, where as the number of dimensions increases, the number of training points, these red points that you need to fit the curve properly in a way that generalizes nicely, grows exponentially with the number of dimensions. So learning in high dimensions is fundamentally a cursed estimation problem. This is sometimes also known as the curse of dimensionality. Obviously, the kinds of functions we have to fit in general deep learning problems may be way more complicated than one Lipschitz functions. So this is just even a very simplistic case. So one potential response to this is, okay, if high dimensional learning is hard, why don't we just do low dimensional learning instead? We understand that quite well. There's a lot of very strong theoretical results in this space. And in some cases, you might be able to do that. But unless your data manifold is roughly linear, this kind of simplistic projection to a low dimensional space will certainly lose a lot of fidelity in the input. So here you have, for example, various MNIST digits 2, which are assumed to live on this kind of complicated Swiss roll manifold. And as a result of a simple linear projection, you might still be, like MNIST is still simple enough, you might be able to classify these as 2 digits even from a linear projection to a low dimensional space. But you can already see what the digits look like. This kind of filtering operation already loses a lot of the detail and a lot of the fidelity. And for many more complicated tasks that you have to do with natural images, for example, you might lose way too much detail and not be able to make proper sense of what's going on in this input anymore. So high dimensional learning is cursed, and low dimensional learning potentially loses way too much information about the input. So what can we do? Is there something we can do as a middle ground? And this direction leads us to study symmetries, groups, and invariances as a way to capture the inherent geometry of the data, which I'll be talking to you about next. So one way in which we typically ameliorate this problem is by injecting some further assumptions about the geometry of our data through the use of so-called inductive biases. Now, what are inductive biases? They simply restrict the functions in our hypothesis space, so the possible functions that say our neural network can fit, to ones that respect the underlying geometry. And as a result, this reduces the space of solutions and therefore can make our high dimensional learning problem a bit more tractable and a bit less cursed. And there are some very popular examples of these geometric assumptions being used nowadays. For example, if you're working with images, you would typically expect that they should be processed independently of shifts. So you have this picture of a dog, which is transformed in various ways or shifted in various ways. And as a result, that doesn't change the fact that the underlying class is still a dog. Then if you look at data that lives on a sphere, for example, this smiley face, which is located on a sphere, regardless of how I rotate this face along the surface of the sphere, it is still the same smiley face. Like I haven't changed inherently anything about it. So spherical data can often be processed independently of rotations. And an area which is particularly dear to me, graph representation learning, processing data that lives on arbitrary graphs. There are many different ways in which I can choose to present an equivalent graph to you. Here I've given two tiny examples of two graphs, which if you stare at them for long enough, you'll see they're actually exactly the same graph, just presented in a slightly different way. And what we actually want is when two graphs are isomorphic in this way, we would want our graph neural network to give us exactly the same outputs for these two different graphs. So clearly, there's a lot of very interesting information about the geometry of data that we can exploit to make the space of possible neural networks smaller and therefore easier to control. And what we're going to be doing throughout the book and throughout this talk is try to formalize this, try to make it a bit more formal. So before I dive into the elements of formalizing this blueprint, I'm going to just introduce some mathematical notation elements to make sure that we're all on the same page with the notation I'll be using. So we're going to assume that our data lives on a certain domain omega. And for example, if we're looking at images, different elements of omega are going to be pixels. If we're looking at graphs, different elements of omega will be nodes. And typically in representation learning, we're interested in featurizing the domain, that is attaching some feature representations to every single element of the domain. And therefore, we need to assume some kind of a feature space C for every element of the domain. And for our purposes and the way deep learning is typically implemented, this feature space will be just k-dimensional real vectors. Once we have a domain and a feature space, we can talk about what it means to featurize a domain. And we just have to define a space of feature functions x, where individual elements of x are functions that take elements of the domain and give back the feature vector for that particular element of the domain. Now, one thing that's very convenient and will pop up time and time again throughout this talk is that very often our domains will actually be discrete. And as a result, I don't need to think about this x as a function. I can just interpret it as a feature matrix, capital X, which is a real matrix where the number of rows is equal to the number of domain elements and the number of columns is equal to the feature dimension. So the ith row of this matrix will tell you the features of the ith node of the domain. This is very convenient for us because we're going to be able to, for most cases, stay within the realms of linear algebra, where deep learning is usually most naturally talked about. Okay. Now, this sets up some of the main preliminaries. One other thing that I will mention in case that we manage to get far enough to talk about how to define convolutions on spheres is that if you have an appropriate metric over this domain, you can also define the notion of inner products over two feature functions over the domain. So this is at the bottom of this slide. Imagine I have two feature functions, x and y. I could compute their inner product as integrating over the entire domain of pointwise inner products in the feature space on all of the domain points, where I'm integrating with respect to the measure that's appropriately defined over that domain. But once again, this will not become relevant until maybe when we start talking about convolutions on spheres. So now that we have set up these key building blocks, let's talk about these guiding principles of how do we exploit the geometry in data. And one very important concept here is the concept of a symmetry. So a symmetry is a transformation that takes domain elements to different domain elements, and it leaves the underlying object invariant. We assume it doesn't change the object. Now, the very fact of me saying that it leaves the object unchanged implies a ton of properties that these functions must have. In particular, if I have two different functions that I consider symmetries, I should be able to apply one, then apply the other, and still get the symmetry because neither of them have changed the underlying object. So symmetries by design must be composable. Then they also must be invertible, because if I cannot invert a symmetry, then that means I've lost some information about my object, and as a result, it hasn't left the object unchanged. And also, by definition, the identity transformation must itself be a symmetry, because an identity by default will not leave an object in a different state. And once you collect all of these different properties, you'll realize that we can reason about all these symmetry functions using a very elegant mathematical object, which is the group. And the elements of these groups are going to be individual domain transformations. So group elements G will be functions taking domain elements to different domain elements. And here, just to kind of illustrate this, assuming you don't deeply work in group theory, on the left-hand side, I've just listed all the standard axioms of a group alongside, which is a set of these symmetries along with the binary composition operation. So it must be, the group must satisfy associativity, invertibility, closure, and the identity symmetry. The identity function must by default be a symmetry. And here on the right-hand side, I've illustrated a very simple symmetry group over the domain of triangles, where I store features in the 3 nodes. And under these particular triangles, I'm allowed to do either horizontal flips or rotations. And as a result, I'm changing in which node I'm storing which features, but I'm not changing the underlying triangle object. So in this particular case, the individual nodes of a triangle are elements of my triangle domain, and the rotation operation or the flip operation is an element of my symmetry group. So this is kind of trying to just link back the different concepts to the setup of the group theoretic description we're going to use. Okay, so once we have these different symmetry groups, what we're curious about, so we can reason about how they affect the data, we need to be talking about something called a group action, which is just an operation that takes a group element, a symmetry transformation, and a domain element, and applies the appropriate transformation to that domain element. For example, in the case of images, it could be some kind of translation, or in the case of sets, it could be a permutation. And in particular, we will be interested in group actions that are linear. That is, if I apply a group action on a linear combination of featurizations of my domain, x and x prime, I can get exactly the same effect as if I first perform separately the group action on the 2 featurizations, x and x prime, and then linearly combine the result in the same way. It's going to be sufficient for us to look at linear group actions because, first of all, in deep learning, we typically introduce nonlinearities in a slightly different way through activation functions, and I'll get back to that in a bit. But also because, once again, it allows us to stay entirely within the realm of linear algebra, and we can represent linear group actions using an appropriately chosen n by n matrix. So we have this mapping rho, which takes every single one of our symmetry transformations and gives us an n by n matrix, which has the effect of when you left multiply it by the featurization of the domain, you get exactly the same effect as if you applied the group transformation to the domain. So that's going to be a very important concept because now I can use it to completely, in terms of linear algebra, define what are the properties that we would want our functions to have to stay resistant to these symmetry transformations. And this brings us to the notions of invariance and equivariance, which are the central topics in our write-up. So first, the notion of G invariance. We can restrict our function, say our neural network that takes signals on the domain omega, to some predictions on the level of the entire domain y, to be invariant to the symmetry group if, no matter what group action row of G I choose, that doesn't change the output of the function. So the output of the function is unaffected by performing the symmetry group actions on the input. One example of this is an image classification, where, as I said, output class is assumed to likely not depend on shifts of the image. However, invariance gives us a way to get predictions on the level of the entire domain, but sometimes we're not interested in predictions on the level of the domain. We're actually interested in predicting individual domain elements on every single one of them. And for that, invariance is not quite what we need, because when we get a prediction on the level of the whole domain, this invariant operation actually destroys some of the information about the individual domain elements. So actually what we want is this more fine-grained notion of G equivariance, where we have a function taking signals on the domain to different signals on the domain. And we say that it's equivariant if I have any group action. And now, as a result of applying the group action, this might change what I get as a result of applying the function, but it changes in a very predictable way. Specifically, any group action I perform on the input would affect the output in exactly the same way. And one example of this is in image segmentation. So now I have to predict an object class for every single pixel of my image input. And there, if I perform, say, any shifts to my input, I would expect my segmentation mask to follow exactly the same shifts. So we can formalize this by forcing our function to be equivariant to shifts. Now, invariance and equivariance are two very powerful concepts, and we've based most of our blueprint on the two of them. However, there is another principle which is super important for making deep learning architectures that are efficient and robust in practice, and that is the principle of scale separation. Basically, while invariance and equivariance allows us to be resistant to pure symmetries, so here, for example, you have an image of a house, and if I perform a symmetry transformation to it, like this shift, I can still recover exactly the same picture of a house, and I would ideally want to not have to relearn that kind of rule, but bake it into my architecture, so that's great. But in many ways, we're dealing with data where there's some noise imposed by nature, and nature doesn't always act in purely symmetric ways. In fact, there is often some noise being introduced, some distortions. So here you have this slightly wobbly image of that same house, which hasn't undergone a symmetry transformation. Like, some information has clearly been distorted when you've transformed the image in this way. Yet you would still kind of want your model to be robust to reasonable levels of distortion, because there will always be some level of distortion when you're working with natural data. And you have to be careful, because if you just impose invariance or equivariance to your functions, that still doesn't solve the problem of, if I have a distortion somewhere, my output signal might blow up as a result. And what we derive in the book through a combination of various known theoretical results is that actually it's probably highly beneficial to do super local operations on the domain and then compose them to model larger scale ones. The reason why we want to do that is because if a layer is local, then any error or noise that happens in the vicinity of a particular domain point will not globally propagate immediately. It will actually stay locally contained around that single point. So that's one motivation for why convolutional neural networks are often designed with very tiny 3x3 convolutional kernels, but then made super deep to propagate the effects. And accordingly, any geometric deep learning layers we make would ideally be local. And one comparison here for people who might come from signal processing is Fourier transforms versus wavelets. Both of these give you a basis which you can use to parameterize any particular function of interest, invariant and equivariant as well. but Fourier transforms do it in a way that spans the entire input domain. So if there's any distortion anywhere, these sines and cosines will propagate it all over the domain immediately after applying a single layer, whereas wavelets are nice and localized and actually zero for most of the input space. So as a result, any local distortions will not globally propagate. So combining these two key principles, the idea of invariances, equivariances, and scale separation, brings us to define the key building blocks for our blueprint of geometric deep learning. And here I've just outlined the 4 key elements. I will kind of just repeat the two main ones that we already talked about. So equivariant and invariant layers. As mentioned before, it's fine for us if these equivariant functions are linear, because we have a different way of imposing nonlinearity, and it's going to be much easier to reason about them in this way. So group equivariant linear operations that are also typically also assumed to be local. That is, the outcome of these equivariant linear operators will only depend on the domain elements which are in the vicinity of a particular domain element, in the sense of some underlying metric over omega. And this is great if we want to get signals on every single domain element as outputs. In case that we want to predict something on the level of the entire domain, we can actually stick in a global pooling layer or a group invariant layer at the very end, which gives us a prediction on the level of the whole domain. Now, the reason why it was totally fine for us to stick to linear group equivariant operators is because in deep learning, we will often impose nonlinearity through an explicit activation function, which is just a nonlinearity applied to every single feature dimension in isolation. And things like sigmoidal functions, rectified linears, and so on. And actually, it turns out that this is totally enough, because combining, there are already some well-known universal approximation results that show that when you take some of these equivariant linear operators and compose them with pointwise nonlinearities, this is already enough to represent all kinds of well-behaved real continuous functions over that domain. So the combination of the two is sufficient to model everything that deep learning would require. And finally, one thing that I'm not mentioning in a lot of detail here, because in a way it depends a lot on the underlying geometry of the domain, but it's super useful if you have to predict signals on the level of the domain and the domain has a very high resolution. Periodically, it's quite useful to downsample that domain while you're processing it. And this is the basis of, say, local pooling layers that you might see in images, or even like in manifold or mesh applications. So that means that at every step you pick a domain omega j plus 1, which is contained within the previous one, and you essentially do a sort of downsampling on the original feature space into a coarsened domain. I'm not covering them here in detail, but coursing layers also follow from this principle of scale separation. So now what we're doing is we are composing all of these layers together in ways that make sense, such that the output space of one attaches to the input space of the other. And when you combine these equivariant local pooling layers and potentially invariant layers at the tail, if you want a prediction in the whole domain, it turns out you get all you need to build the deep learning architectures that are all you need, at least based on the state of the art in deep learning in 2020. In our book, we show that all of the fan favorites, such as convnets, graphnets, deep sets, transformers, and LSTMs, can be derivable based on the principles in this blueprint. You just need to have the right choice of domain and the right choice of symmetry group to be invariant or equivariant too. But what's, in my opinion, also the quite exciting part of this blueprint is the fact that it also allows us to squeeze in many neural network architectures that don't quite lie on these popular domains, but some more interesting geometric domains, such as spheres or manifolds, where you get architectures such as spherical CNNs or mesh CNNs. And we find that those can also be nicely explained by the ideas within our blueprint. So the hope is essentially that through our blueprint, we're going to be able to not only categorize the existing research in deep learning, but also drive or synthesize research in deep learning going forward to potentially more interesting or exotic domains. And on that note, this basically wraps up the first half of the talk, where we introduce the blueprint and the main concepts of invariance and equivariance. And in the second half, we're going to talk through some of the 5 Gs of geometric deep learning. Specifically, in the book, we cover 5 instances of this blueprint of particular interest: grids, groups, graphs, geodesics, and gauges, which covers aspects of, say, image data, homogeneous groups such as spheres, graph structured data, and also various kinds of mesh or manifold data. Now, in this talk, I don't really have enough time to go through all 5 of them. So what's going to happen is we're going to illustrate and concretize all these concepts using the domain of graphs. And then I'll probably skip over grids because convolutional neural networks are a fairly common and established model nowadays. And I was only really using that part to link it a bit more to Fourier analysis. And ideally, if we have a bit of time at the end, I will show you how to generalize the blueprint from grids to spheres and derive a convolution operation over spheres. So before diving into graphs, I think this is a good point to take a short pause and just see if there are any questions or misunderstandings about what I've said so far, because what we're going to do when we analyze, say, the graph case, is going to link back to this blueprint through and through. So, are there any questions that that you would like addressed now, or basically, is there anything that you would like explained in more detail before we dive into graphs?
There are a couple of questions in the chat. Let me read them out. So I think this refers to, I think just before section 3. In the equivalent function definition, why are the 2 spaces similar?
Equivalent function definition. I'm not sure what is being referred to because I don't think I talked about equivalent function. Oh, equivariant. Yeah.
I would guess so. I think the question was asked just before you went to section 3. So I think it was like the last slide of section 2. So I think that was.
So basically this, I guess. Oh, right. I assume it's referring to the input and the output space of this function. So I think that they don't in principle. These 2 domains and function spaces do not have to be exactly the same, but for the purposes of deep learning layers, usually equivariant layers will not change the underlying domain, and they will stay within the same feature space. But I think in principle, they don't have to be exactly the same. Yeah.
Okay, thanks. Someone's asking, does your activation functions include ReLU?
Yes. So ReLUs are included in the activation functions. They're basically the most standard choice nowadays. Yeah, and many universal approximation results that we have for sigmoids, I think we also have them for ReLUs.
Okay. Philip's asking one question: why is invertibility a natural consequence of transformation, keeping an object unchanged? On this example, so for example, in the context of image classification, if we have a data set of images within a picture frame which may be localized to the outer pixels, then I could replace the frame by a generic frame without affecting the class, yet the operation is not if we have more than one type of picture frame.
Yeah, so this is I think this is a very, very important question. What I would say is that surely we can define a different set of transformations that leave objects unchanged, but are in principle not invertible, because if all we're ever doing is changing frames and we know there's nothing at the boundary of the image, then yes, in principle, we can do something like this. I guess the main thing that I'm saying is that if we start from a very abstractified point where all we know is we're dealing with data that lives on, say, a grid domain, and we want to be invariant to the transformations, we cannot upfront assume that our output class will never depend on the outer pixels. That's not part of the definition of the grid domain. Like, if all I'm saying is my output class may depend on like any part of my input grid, then I cannot say that the operation of changing the frame is a symmetry transformation. Like, that would require a bit more knowledge. And in this particular case, yes, invertibility is not does not come naturally, I guess. But then in that case, you know, if your output doesn't depend on the grid itself, then like the central part of the grid at least, then I assume you could, without loss of generality, completely ignore those frame pixels anyway, and then still define a symmetry group over the part of your image that actually matters. So I think this doesn't violate the invertibility assumption in itself. But no, it's a very good point. And there are certainly some cases where maybe you can get away with like a set of transformations that does not assume invertibility, but then obviously the concept of groups is not going to be the right one to capture these kinds of transformations. So I hope that answers the question to a reasonable standard. Yeah, okay, great. All right, so I will move on now. Oh, sorry. Mm-hmm.
So there's one more question. Someone's asking, please confirm this applies to natural language sequences of discrete alphabets.
Yes, so we can definitely apply this to natural language as well. In fact, LSTMs, which used to be a very popular model for natural language processing, are applied over the 1D grid domain, and therein, you know, we have shown that through some principles such as time warping invariance, you can rederive the whole class of gated RNNs. So this definitely applies to natural language, and of course the transformer model, which is in use nowadays a lot in natural language, fits very nicely in our blueprint, though amazingly it doesn't fit under sequential models, it fits under graph models, and the way you inject the sequential information is actually quite implicit, actually. Like, you're not assuming your domain is a grid, you're actually just plugging features that sort of tell different nodes in your graph that they're located on a grid. So definitely applies, but not always in the correspondence to sequences, I guess. Because just to be clear, in natural language, a sequence is usually not the best way of looking at things, because words don't just interact in a sequential order, right? You have, say, a subject and object relationship, but the subject and the object can appear in wildly different parts of a sentence. And ideally, you'd want to have some link between them, right? Transformers do this very standard assumption of, if I don't know what the connectivity graph between my objects is, let's just assume everything is connected and let the network figure for itself what the key connections are. And that's why under our blueprint, transformers fit most naturally as operating under a complete graph of words rather than sequences of words. So yeah, I hope that answers your question. Thank you.
Thanks very much. Yeah, that was all the questions.
So let's dive into the graph domain. And actually, I'm not going to start with the graph domain. I'm going to start with something even simpler than the graph domain, which is the domain of sets. So the reason for this is that it's going to be much easier to analyze. Most of the conclusions we'll get mathematically will carry over to graphs, and even if you just look at data which comes in the form of unordered sets, it's still data which has a lot of potential real-world relevance. Some key examples here are point clouds, or the kinds of data you get from self-driving vehicles. So we're going to start by assuming we have a graph with no edges. So our domain omega will just be the set of nodes V. And we assume we're going to featureize the domain. So we have xi representing a feature vector for the ith node in this set. And we can then, what we typically do in deep learning on sets is we stack these node vectors into a node feature matrix of shape n by k, where n is the number of nodes and k is the feature dimension. And that means that the ith row of this matrix will correspond to the features of the ith node. And very important point here is that the moment we have done this, the moment we put the nodes in this particular stacked order, we have specified an ordering of the nodes, and our fundamental assumption when working on set data is that the nodes are unordered. And we would actually want the result of any neural network applied over this feature matrix X to not depend on the specific order we chose. And in mathematics, we have a very nice way of reasoning about what are the operations that change the order of the nodes. That is the concept of a permutation. And for a set of n elements, there are n factorial many of them. And what's very convenient is that we can stay completely in the realms of linear algebra when talking about permutations, because every permutation defines a unique n by n matrix called the permutation matrix, which has exactly 1, 1 in every row and column, depending on the specific layout of the permutation, and 0 everywhere else. And here you can see on a specific example, the only effect that this permutation matrix has when you multiply it with a node feature matrix like the one we constructed before is to permute the rows of the node feature matrix. And that's it. No other transformations are happening. Now note that I've specified a linear algebra version of my group action through this permutation matrix. So the row mapping that I talked about before is in action here. So row is something that would take a particular permutation like 2, 4, 1, 3 and spit out an n by n matrix with the right layout that has the same effect as permuting the rows of that matrix. And now that I have the notion of a group action for permutation, I can invoke the blueprint pretty much directly. So I want to design functions like neural networks f over these unordered sets of nodes that will not depend on the order. What does this equivalently mean? If I apply a permutation matrix, that shouldn't modify the result. So this gives us a useful notion of permutation invariance. And we say that our function f of x is permutation invariant if no matter what permutation matrix P I choose, it doesn't matter if I apply it to the input, the output is still the same. One very generic form of a permutation invariant function that respects these constraints is the so-called deep sets model that was presented at NeurIPS 2017. And in a nutshell, it performs this function f by first independently transforming every single node feature vector with this shared function psi. Then you perform a permutation invariant aggregation, such as summing of all of these feature vectors. And then potentially, if you want outputs on the specific outputs on the level of the whole set, you can additionally transform this with another function phi. So these psi and phi functions are just typical multi-layer perceptrons. And the critical part, which gives this functional group a form of permutation invariance, is the summation, because the outcome of the summation will not depend on the specific order in which you chose to stack the vertices. And it also means that you can use other kinds of aggregation functions like maximization or averaging, and it would still have the same properties. Now, as we discussed before, invariant models are a great way to obtain outputs on the level of the whole domain. So in this case, outputs on the level of the whole set. But if we wanted answers at the level of individual nodes, well, this isn't quite helpful because we still want to be able to identify outputs on the level of individual nodes, and this permutation invariant layer would destroy that or make it hard to recover. So instead, what we might want to seek are functions that do not change the order of the nodes, but otherwise might give us different results for different orders. And specifically, if we permute the nodes, it shouldn't matter if we do it before or after applying our function, which gives us the notion of permutation equivariance. Once again, directly following the blueprint, a function f is permutation equivariant if no matter what permutation matrix I choose, it doesn't matter if I apply it to the input or I apply it to the output. I should get exactly the same results. And now here we also want this notion of locality, but in unordered sets, we actually don't have any upfront assumptions on which points are local to which other point because they have no relation between them. And in this kind of setting, the only thing we can do to ensure equivariance and locality is to transform each node's feature independently through this shared function psi. So hi is equal to psi applied to xi. And in principle, to get the full equivariant layer, you would have to stack these h's into an output matrix h. But especially when we move on to graphs, it's going to be super useful to think about these transformations, equivariant transformations, in terms of how they affect individual domain elements. So we'll stay on the level of hi. And now combining this, so this gives us the equivariant part. If we end up wanting something on the level of the entire set, we can just stitch a permutation invariant aggregator on top of everything, and then add some permutation invariant tail function. And you can see how our geometric deep learning blueprint is directly invoked in the case of sets. So you have the equivariant part, which transforms every node in isolation. And in case you want outputs on the level of the whole set, you need to add a permutation invariant aggregator. This O+, whenever you see it, I'm referring to something like sum, average, or max, and an extra function on that aggregated output. Now, a very important remark here is that this is typically as far as we can get with sets. If you don't assume or infer any additional structure, this is as far as we can get for local permutation equivariant functions on sets. So now we can move on to the case where things get a little bit more interesting. And we don't just have sets, but we also augment these sets with edges between them, giving us graphs. And there's many ways we can represent this edge structure in a graph, but because we want to stay within the realms of linear algebra, I'm going to be using the adjacency matrix to represent the edges. So an adjacency matrix A is, in our case, just a binary matrix such that all the ij elements that are linked by an edge will have a 1 and the others will have a 0. So the adjacency matrix is of the shape number of nodes times number of nodes. And if you've done some graph representation learning before, you might know that there's some other interesting things we can attach to this, like edge features or even real valued edge weights. These are all possible. They do not change the underlying conclusions. They make the math a little bit more verbose. So just for the sake of simplicity, I'm going to be ignoring those kinds of data, and I'll just assume that edges are a binary thing. Either an edge exists or it doesn't. And our main desiderata, permutation, invariance, and equivariance, still pretty much hold in this case. The only difference is that whenever I permute my node features, I now must accordingly permute the edges. And if I choose to represent the edges with the adjacency matrix, and the adjacency matrix is of the shape nodes by nodes, this now means that I must permute both the rows and the columns of the adjacency matrix. So when I apply permutation matrix P, this will amount to PAP transposed in linear algebra terms. So we arrive at exactly the same definitions for permutation, invariance, and equivariance as we did for sets. The only difference is in the fact that now the adjacency structure is a non-trivial part of the domain, so it must be part of the input to the function. And whenever I did a permutation transformation on the nodes, I must also do an appropriate transformation on the rows and columns of A. But otherwise, the setting is exactly the same. Invariant graph functions should give me the same result regardless of whether I've permuted the graph. Equivariant should give the same results regardless of whether I've permuted the graph before or after. And there's another very exciting thing we can do on graphs that we were not able to do in the case of sets. And in particular, we can do a more fine-grained notion of locality, because now we have a nicer context on what could be local to a particular node, and that is that node's neighborhood. So for a particular node I, its one-hop neighborhood is defined as all of the vertices j, which are linked to I by an edge. And once you have these nodes, you can also extract their features. So the set of neighborhood features, x and I, is the set of all feature vectors which are of the nodes in the one-hop neighborhood. And now I can define my local function, g, as operating over that set of neighborhood features. So g takes as input the features of a particular node, xi, and the features of all of the neighbors, x and I. And once I have a function g like that, I can construct permutation equivariant functions by just stacking the results of applying g to all the individual neighborhoods. So the only remaining piece that we need to ensure that f is equivariant is because g depends on the whole set of neighbors, it shouldn't depend on the order in which we present those neighbors. So as long as g is permutation invariant, we can guarantee that f will be permutation equivariant. Now, this was a lot of terms thrown together in rapid succession, so I thought it would be really nice to just visualize everything that I just said. And as a result, this is what we've done. So we've defined a local function, our GNN layer G, which operates on features of a central node and all the features of nodes in the immediate neighborhood. And as a result, gives us updated feature representations H for that node. And that's then applied in isolation in a shared manner to every neighborhood. And this gives us the updated featurization of the graph. Once we have a graph neural network like this, we can apply it to a particular graph which has some inputs, input features X and adjacency structure A. Applying the graph neural network layer, as we described, will update the features of every single node of the graph while preserving the adjacency structure. And once we have these latents, what can we do with them? You can either classify or regress individual nodes by learning a shared classifier on every node's features. If you want to predict something on the level of entire graphs, we follow the geometric deep learning blueprint once again and use a permutation invariant tail to aggregate all these nodes together. For example, by summing them up and then learning a graph classifier on top of those summed features. And one thing that's a bit unique to graphs is you can also predict properties on the level of individual edges, which are now domain elements too. And you can even predict existence or absence of edges, which is known as link prediction, by learning a classifier over the relevant node features and potentially any edge features that you might have between them. Now, I've told you everything about GraphNets except for how exactly we define this function G, which performs the aggregation over the neighborhood set. And this is without a doubt one of the most active areas of machine learning today. So it's very hard to summarize it, but what we found in our book is that fortunately about 95% of the layers proposed nowadays can be fit into one of these three spatial flavors. Convolutional, where the interaction weights are fixed in a weighted combination based on the topology of the graph. Attentional, where the interaction coefficient is learned based on the features of the sender and the receiver node. And finally, message passing networks, where rather than computing weighted combinations of neighbors, you actually have the neighbor and the receiver collaborate to compute a whole message vector to be sent to the receiver, and then the receiver aggregates them. There's obviously a lot more that can be said about just graph neural networks, and if they're a bit newish to you and you want to find out more, I recently gave a 1-hour talk just on the theoretical foundations of GraphNets, and that one is publicly available on YouTube if you'd like to take a look after this talk. Now, I realize that we only have about 5 minutes left, so I'm going to skip over grids for sure. With groups, I'll also skip the blueprint, which allows us to define convolutions over spheres. And yeah, unfortunately, I'll also have to skip over a quick rundown of how we might generalize this to arbitrary manifolds and meshes through the key idea of parallel transporting a filter along the surface of the manifold. But there's a lot more details than this in the actual write-up, so I would very much invite you to take a look at this. Our write-up is publicly available at geometricdeeplearning.com, and there you can see not only the paper, but also accompanying blog posts, and also Michael Bronstein's keynote at iClear 21, which explains a lot of these concepts from a slightly different perspective. And you can also contact us if you spot anything. The book is still very much a work in progress. We're at about 160 pages now, and we're hoping to have a final version ready by, say, start of next year. So any feedback is highly appreciated. And on that note, I'd like to thank you very much for listening. And I'd like to thank all of my co-authors once again, Jean, Michael, and Taco. We'll be happy to answer any questions in the time we have left. But if you have any questions you'd like to discuss offline, feel free to reach out to me either via email or via my social networks, which you can find on my website. So thank you very much.